Hello, Rice. In lesson 7.2, we talked about using a formula to figure out the future value of compound interest. We didn't want to mess around with charts anymore. And what we discovered, carried forward from 7.1, was that the amount of a lump sum in a compound interest situation is your principal multiplied by 1 plus your compounded interest rate, or your interest rate per compounding period as a decimal, raised to the exponent the number of compounding periods. So to review, this is your amount, or sometimes called your future value, the value in the future. Future value. For that reason, you want to be careful about using the word value to mean like how much interest you get. Principal, I'm not going to say, oh, this is the, well, okay, so we can use the word value here, but we need to use a time reference on it. It is called your principal, or because we're in a lump sum, we can call this the present value. Even the words, the time labels, future value and present value, can cause confusion because I should be able to figure out how much I need to invest, or how much someone would have had to have invested 5 years ago to earn this much today. So this might actually be, this might be in the present, and then this would be in the past. Okay, so think of time as being relative, I suppose. Lowercase I, your compounded interest rate, or your interest rate per compounding period. I'm going to write that one. I like that one better. Interest rate per compounding period. We had period. There we go. And lowercase n, the number of compounding periods. So the little formulas we developed in class to sort of complement these were, if you are getting if they're advertising R% per annum, and you are earning interest F times per annum, that will be your new compounded interest rate. If you are investing for T years and you are compounding F times per year, then the total number of times that you're compounding is going to be n equals t times f, where in both of these, I'm not sure how popular this letter is, but I sort of like using it. F represents your frequency number, so the number of compounds per year. Compounds per year. Okay. So what I want to do for this video is just show you what happens when we increase this frequency. So what we're going to do is just a bunch of repeated calculations, and then we'll check our calculator skills as well. So let's say determine the future value, or the amount, and we're going to keep our principal constant. Let's say that we can put away $100 today. We'll pick a pretty gentle interest rate, invested at 5% per annum. Let's say we can put it away for 2 years. And then what we're going to do is we're going to change our compounding frequency. This will be very important for calculus students a little bit later. Okay, because it should make sense that, okay, if I want to make more money, I should always invest more, or I should get a higher interest rate, or I can invest for longer. Now, in a lot of these situations, my hands are tied. Okay, if I had more money, maybe I wouldn't need to make more money, so why would I be investing? Me working harder doesn't actually get me a better interest rate that much. I could do research, I suppose, and I could wait longer, I suppose. This is one area where students have a huge advantage, just in the amount of time that they have available to them. It's your most valuable resource. Don't squander it. And then something else I suppose that we could try negotiating on is how often, how frequently we compound. So let's try going annually, semi-annually. Quarterly, monthly, and let's jump to weekly. And then let's pretend that we could find an investment that gives me interest daily. Okay. So we should have had an opportunity to play around with a couple of these frequencies in class, but we usually switch the numbers around. And in today's example, or in this video's example, we'll see the actual impact of changing your frequency. Okay, so we're going to substitute into this formula right here, and I'm going to show you our calculations. I don't mind showing the calculations right in the middle of the formula. For annual interest, let's see, I'm investing $100. I'm earning 5% per annum, but I am compounding 1 time per year. And I'm investing for 2 years, but I calculate interest 1 time per year. So the division by 1 and the multiplication by 1 here doesn't do that much for me. We type this in, we get 100 times 1.05 to the exponent 2. And yeah, $110.25. Let's be French and put the numbers on the outside there. So I didn't leave enough room there. Okay, so simple interest, I would have just received $110. Look at that, 25 more cents. Semi-annually. So here's what happens. Your interest rate that you're actually getting is getting smaller. The bank is advertising 5%. You're not really getting 5% per annum. You're getting 2.25 per semi-annum, which is not the same thing as 5% per annum. We're going to see that here. Okay. So your interest rate is getting smaller, but you are calculating interest more often. You have your base getting closer to 1, but your exponent is getting larger here. And we perform this calculation, and we get about, calculator-wise, we should be able to go left to right. I'm going to try left to right for first couple, and then I'll show you sort of like steps on the others. 100 bracket 1 plus 0.05 divided by 2. I'm going to close my bracket, raise that to the exponent. How about we do this calculation ourselves whenever possible? So I don't need the calculator to do 2 times 2 for me. I know that that's 4. Because I don't want to raise to the exponent 2 and then multiply by 2. This is the correct answer, $110.38, a little bit more money. Right. Mistakes that sometimes students make, let's see, if I do 100 times 1 plus 0.05 divided by 2 to the exponent 4, there are like a lot of mistakes there. I need brackets around my base. I need the exponents off. I think I'm dividing by 2 to the exponent 4 here. All sorts of trouble. Okay. Quarterly, our interest rate is now going to be 1/4 of what was advertised. So we're getting less interest, but more often. Let's do investing for 2 years, 4 times a year. Let's try a different combination of buttons for the calculator. I'm going to go left to right, and then I'm going to use brackets for my exponent. 100 bracket 1 plus 0.05 divided by 4. Close my bracket to the exponent, bracket 2 times 4. Just in case I don't know what 2 times 4 is. $110.45. So notice these values aren't jumping. They're not becoming much, much larger. Which is really why, like, negotiating with the bank, as far as your frequency goes, doesn't do much for you. But there are some other advantages as well. Okay. The interesting thing, and this is a bit of a teaser, I suppose, for a calculus student, is that there is a limit to the advantage that you can get. If your frequency is getting higher and higher and higher, your interest is getting smaller and smaller and smaller, and your exponent is getting larger and larger and larger, you will be converging on a finite number. Okay, another calculator option. If I have a calculator that does not handle order of operations that well, I might want to sort of help it out. So I'm going to perform the order in the proper order here. I'm going to do 0.05 divided by 12 equals. Now, what you should never do is, if you're going to touch your calculator more than once, you don't touch it, go off to the side, and then write down this number and round that off. Because rounding off these fractions of decimals when you're raising to an exponent 24 can have huge impacts. Okay. Next, I'm going to add 1 to that. Now I'm going to raise that to the exponent. Let's do 24, and I'll multiply that by 100. And there's my amount, $110.49. Okay. Weekly, there we're using 52 weeks in a year. So I might actually want to try writing down some approximations here for you, just to show you how, I'll do it on the last one because I'll have the most room there, how your base is getting closer to 1, but your exponent is growing without bound. 100 bracket 1 plus 0.05 divided by 52 to the exponent, oops, that's times, to the exponent 2 times 52. And we get $110.51. So we are approaching sort of like the maximum return that we can get. Okay, let's do some approximating here, and maybe we'll see if it makes much of a difference. Daily, if we assume that there are 365 days in a year, then we'd be getting 1/365th of 5%, and then we calculate interest, what, 730 times 365. Let's do approximations here. 0.005 divided by 365. Oh, great. So this is in scientific notation here. Let's do +1 and we can see the approximation. So we're getting 100.1.00136.986. So that'd be like 1%. That's 0.1%. We're getting like 1/100th or 13,000ths of a percent on here, but we're calculating interest 730 times. So it's a balancing act, and students sometimes take a guess at this, and it's very hard to be intuitive. Is it better to calculate 5% interest 2 times, or like 0.0013% interest 730 times? It's usually better to compound. Okay. Now, if I did round this off here, I don't know how students would round this off. Maybe they would do 1.00014 to the exponent 730 times 100. I'm getting about 110.76, where if I type it all into my calculator in one go, I get 100 bracket 1 plus 0.05 divided by 365, close that bracket, to the exponent 2 times 365, close that bracket. So you might not think this is a large value, like a large difference. But look at how much I rounded up to a 1/4 here, and the change in my investment is huge. Proportionally, we're talking what, 24 cents here. You might say, well, no big deal, right? But this is because we're investing $100. What if we were investing $1 million? So do not round off. Do not round in the middle of your calculations. Okay, figure out how to use a calculator to get all of the precision, because the calculator does keep more precision than what it's shown. Okay, yeah, and then come and see me at the end of your calculus course when you look at exponential growth and decay, and you'll find that we're close to this sort of special number where that sort of limits the speed at which things can grow in nature here. Okay. Try it out.